In this video, I will be showing a buffer overflow attack on Heap. So let's proceed. Before doing the attack, I will be showing a little bit of how Heap is implemented in the GCC, glibc. So let's proceed. So Heap is just a pool of memory used for dynamic memory allocation. As you know that in this picture, stack grows downward and Heap grows upward. So next, so this is just a comparison between Heap and a stack. Heap management. There are different implementation of Heap, managing Heap. glibc uses either ptmalloc2 or ptmalloc3. In this video, I'll be discussing about ptmalloc2. So let's proceed. The ptmalloc2 is used in glibc, and it uses break and memory map system called software memory from the OS. Mainly, his heap is split into memory chunks of different size and used depending on how malloc and free are invoked. Best fit, or you can say the first fit memory is allocated. There are mainly two types of memory chunks in heap. One is free chunk and one is allocated chunk. Free chunks are stored in a linked list. So let's see. When in a program the first malloc call is made, a heap is allocated. This size of this heap is 132 kilobytes. This is 132 kilobyte is for both either your system is 32-bit or 64-bit architecture. If you are using multiple threads in your system, then for each thread, if a malloc is called, a different heap is created called this heaps are called arena in this picture. So a different heap is created of 132 kilobyte for each thread. In each thread you call malloc. This is the how heap is implemented. So how heap is managed using the functions malloc underscore state and heap underscore. We will not go into more detail of this. Memory chunks, as I told you, there are allocated chunk, free chunk, and there are top chunk which is not allocated to any free chunk, but they are just they are not used chunk, or not used chunk are stored in the top chunk. We'll talk about last minute chunk. So I told you about ptmalloc2, and this is the structure of allocated chunk. So if a chunk is allocated, there is a metadata. When malloc function is called, malloc return this pointer. Malloc returns us this pointer, and here we can store our data. And before that, if a system is 32 bits, then 8 bytes of memory is used for metadata purposes. And if a system is 64 bit, then 16 bytes of memory is used for metadata purposes. In this picture, you can clearly see that this P flag, there are 3 flags like P, M, and N flag, and this is the chunk size. This whole chunk, size of this whole chunk is stored here, and the P flag tells us about if the previous chunk, as we know that linked lists are stored in the circular list, and then the P flag tells us about that if the previous chunk is in use or free. So if the P bit is 0, means previous chunk is not in use, then this memory here contains the size of the previous chunk. Okay, next, this is a structure of a free chunk. So you can say this is the metadata for the memory chunk. There are these two new pointers, like forward pointer and back pointer. So as you know that memory chunks are stored in a linked list fashion. So forward pointer indicates to the points to the next chunk in the list, and back pointer points to the previous chunk in the list. So you can see that this is our suppose this is our heap. The orange ones are the allocated chunks and the blue ones are the free chunks. So as you can see that this is our free chunk, and the forward pointer of this chunk is pointing to the it is stored in circular fashion, so circular linked list fashion. So forward pointer is pointing to the previous chunk, and backward pointer is pointing to the previous chunk. So In ptmalloc 2, memory chunks are, as you can, we say that is stored in form of bins, like this. In a form of that it is stored in the form of linked list, but there are different type of links. For that, this linked list contains only memory chunks of 16 bytes. This linked list contains 20 memory chunks of 24 bytes, and so on. Different lists are maintained so that we can minimize fragmentation, and speed of allocation and free we can increase. There are different type of bins are managed for that. There are mainly four type of bins. There is fast bins, unsorted bins, small bins, and large bins. Fast bins are 8 byte chunks, and as you can see that they store fast bin contains 16 bytes chunks, 24 bytes chunk, 32 bytes chunk, and so on up to 80 bytes of chunks is contained in the fast bin. It is a singly linked list. Different bins use different different type of linked list. Fast bin use singly linked list. So this is the inside example of a fast bin. So as you can see, this here it contains 16 bytes of the free chunk, 16 bytes of free chunk. Here it contains 32 bytes of free chunk. Here it contains 64 bytes of free chunk, and so on. Here's an example of file. So in this example, as you say that there are two memory allocations. First, X is allocated 15 bytes and Y is allocated 13 bytes. So what happens that they both of them will end up in the same bin. So what happens that X is allocated 15 bytes, then you see here the address of X, then X is freed. So X is freed. So when the next allocations happens, you see that the Y is also allocated the same bin. So Y is also allocated the same. So what happens that this memory is first allocated for X. Then when this memory is freed, X is freed, this memory is this free chunk is appended to the unsorted bin. We'll talk about that in unsorted bin. And when the next malloc function is called, then what ptmalloc does is it searches the unsorted bin for the first fit, like which the memory which has been recently used. It checks that if it can also be used or not. So here you can see that the Y has also got the same address as X, and here you can see that X has been allocated 8 bytes and Y has been allocated 13 bytes, and they both end up in the different bins because of the fast bin implementation. There are unsorted bins, as I told you. Unsorted bins use doubly linked list. The chunk size are not fixed, and any size of chunk can be inserted in unsorted bin. And whenever a chunk is freed, whether they belong to fast bin, small bin, or large bin, it is first inserted into unsorted bin. And when a next malloc is called, the ptmalloc first searches in the unsorted bin and see if any recently used chunk can be reused. This is the internals of the unsorted bin. As you can see, there is no fixed size. Here size is 104 bytes, then 1008, and as you can see. Now we can ignore this. Now there are small bins. There are 62 bins inside small bins, and they also has a chunk of, use the chunk of 8 bytes. Then there are large bins. Large bin contains 63 bins, and each bin has a circular doubly linked list, and these bins are stored in the decreasing order of size. And as I told you, the top chunk, the memory remains after used in these bins are kept in the top chunk. So if ptmalloc, when a malloc function is called, ptmalloc searches for all the bins, and if the user request cannot be fulfilled using these bins, then it goes to top chunk. If top chunk memory is larger than the requested memory, the top chunk is splits it into the user chunk, and user chunk is allocated to the malloc call, and the remainder chunk is kept in the last remainder chunk. And if the top chunk also is not able to satisfy the user request, then Then break and as break function system calls are used to get a new chunk of memory from the OS. So that was our implementation of the how heap is implemented in glibc.